Hello, I'm Maggie Amoncho, and I will be presenting the function and relevance of augmented reality as a platform technology. Background and context. Augmented reality technology has emerged as a disruptive force across various industries, including healthcare, military, and retail. With increasing adoption, AR applications face significant challenges related to operating system support. Specifically, these systems must manage complex resource demands, handle real-time processing, reduce latency, and optimize energy consumption. As AR systems evolve, the role of OS-level support becomes crucial for ensuring that these applications perform optimally across different platforms. Research into OS support for AR applications has lagged behind, creating a significant gap in understanding how OS architectures can be optimized to meet the specific needs of AR technologies. Research problem. This presentation explores the challenges that operating systems face in supporting AR applications, focusing on issues related to latency, sensor fusion, resource management, and energy efficiency. The main research problem addresses how OS-level support can be enhanced to ensure that AR applications perform smoothly and efficiently, particularly in multi-application environments. Despite the growing popularity of AR, there is insufficient research on how operating systems can be optimized for these unique challenges. So for the significance of the study. The significance of this study lies in its potential to contribute to the development of better OS solutions for AR applications. By identifying and analyzing the gaps in OS support for AR, the study aims to guide future development of operating system level optimizations that can enhance user experience and performance. This research has the potential to impact several sectors, including healthcare, military, retail, and more, where AR applications are already in use or have high potential for future integration. An overview of previous research. So previous research, such as that done by Loris Diatoni et al., highlights that the growing challenges that AR systems impose on operating systems. I said that wrong. Previous research overview. Previous research, such as that by Loris Diatoni et al., highlights the growing challenges that AR systems impose on operating systems. Studies have discussed various solutions for improving sensor fusion, resource management, and latency, but few have focused on the OS-level abstractions required for AR applications to work efficiently. Apple Vision OS and Microsoft HoloLens are key examples of platforms that have attempted to address these challenges, but existing research fails to fully address the multi-application demands and real-time processing required in AR systems. This gap in research is a critical area that needs further exploration to develop operating systems for AR. So for a research gap. There's a clear research gap in understanding how operating systems can be optimized for AR applications, particularly in multi-application environments. There is a clear research gap in understanding how operating systems can be optimized for AR applications, particularly in multi-application environments. Current solutions provided by Apple Vision OS and Microsoft HoloLens and AR Core have addressed certain issues, but they fail to consider the broader challenges of multi-user, multitask environments and the need for more efficient sensor fusion and energy management. This gap presents an opportunity to develop OS-level support that can better handle these demands, ensuring improved performance, scalability, and user experience across a wide range of AR platforms. Tools, technologies, and methods. This research uses a qualitative design with document analysis and comparative review to assess the viability of augmented reality operating systems. The data collection is conducted through four main channels: public software development kits, which are of Vision OS and Windows holographic shells; technical white papers and developer guides, which have insights into system reliability, sensor integration, and rendering challenges; and benchmarking reports from the industry, which provide performance metrics including latency, thermal performance, and energy consumption, as well as academic databases where literature will help source relevant research and data for the study. The tools used for organizing and collecting the data include spreadsheets and simple database tools. A comparative analysis is employed to evaluate similarities and differences across platforms. The synthesis of findings from secondary sources enables the assessment of augmented reality operating systems' practicality and relevance in light of evolving computing trends. Presentation of findings. A research paper investigated the viability of augmented reality operating systems by comparing the two major platforms, Apple Vision OS and Microsoft Windows Holographic. Data was compiled and analyzed from technical documentation and existing related literature. Performance metrics such as latency, frame rate, system integration, developer support, and current use cases were the focus of this study. Both platforms have specialized use cases, making them indispensable for sectors where spatial computing adds significant value. However, while mass adoption is limited by cost, AR operating systems platforms should continue to evolve, providing foundational tools for future technological growth. As a comparison with existing previous studies, such as by Nowaki and Woda from 2020, compared ARKit with ARCore, highlighting Apple's strengths in plane detection, frame rate, and lightning estimation. These strengths are further enhanced in Vision OS, and Microsoft's use of depth sensors and holographic processing units align with earlier research, reinforcing the platform's suitability for hands-free controlled environments. The challenges and unexpected outcomes were that despite their technical strengths, both platforms face challenges. Vision OS is constrained by its limited accessibility outside the Apple ecosystem and the high cost of proprietary hardware. Windows Holographic also faces adoption barriers due to its reliance on specialized devices. Additionally, power consumption, hardware bulk, and limited third-party content ecosystems hinder widespread use. Data gathering faced obstacles due to inconsistent or unavailable documentation across platforms. However, secondary literature, developer forums, and academic databases help triangulate findings, ensuring the reliability of results. These challenges demonstrate that while augmented reality operating systems are not obsolete, they are evolving into a more specialized domain-focused tool. Summary of key findings. This research paper examined the viability of augmented reality operating systems by comparing Apple Vision OS and Microsoft Windows Holographic. The study focused on performance metrics such as frame rate, latency, system integration, and developer support. For TLDR, Vision OS achieved 90 to 96 FPS with 11 to 12 ms latency, and Windows Holographic operated with up to 60 FPS and 15 to 20 ms latency. Both platforms provide robust developer environments with advanced spatial computing APIs. The findings demonstrate that while general-purpose AR adoption is hindered by hardware cost and size, platform-specific AR applications are still highly viable. Microsoft HoloLens is used in critical environments like NASA, Ford, and healthcare, while Apple's Vision OS shows long-term commitment to AR evolution, particularly in virtual collaboration and spatial media. Despite technical strengths, both platforms face challenges. In conclusion, augmented reality operating systems are not obsolete, but are evolving into specialized tools for industry-specific applications. Applications and future research directions. So for practical applications, Vision OS plays a crucial role in virtual collaboration and productivity tools, particularly within consumer industries. Its integration with Apple's ecosystem enables the development of immersive, high-resolution AR experiences for tasks like spatial media, virtual collaboration, and creative applications. Windows Holographic, on the other hand, is heavily utilized in enterprise applications, particularly for industrial training, surgical guidance, and remote support. Its robust real-time mapping and gesture recognition capabilities make it indispensable in mission-critical environments such as healthcare, defense, and manufacturing, where hands-free operation and spatial awareness are essential. Future research directions. Research should focus on further developing modular kernel designs to address the high performance and real-time reliability needs specific to augmented reality operating systems. This would involve creating flexible and scalable kernels capable of efficiently handling dynamic AR environments. There is a need for standardized spatial computing APIs that can enhance cross-platform compatibility. This research would enable developers to build applications that seamlessly function across different AR hardware, improving developer efficiency and ecosystem integration. Future studies should also explore the integration of cloud and edge computing to support the scalability and data processing demands of large-scale AR deployments. Leveraging these technologies could offload heavy processing tasks from local devices, reducing latency and improving overall performance. Given the power consumption challenges of AR platforms, developing thermal-aware task scheduling algorithms can help optimize device performance while preventing overheating, ensuring sustained operation in high-demand AR environments. And lastly, research into adaptive rendering techniques would allow AR platforms to maintain visual quality when operating under heavy loads, particularly in complex, resource-intensive environments. And that will be all. Thank you very much.